Chemical shift, what it is and how to measure it. Welcome to the NMR lab with Roy. Magnetic shielding by electrons causes chemical shift and affects the observed NMR frequency. The principle behind NMR is that many nuclei have spin and all nuclei are electrically charged. Nuclei with spin are little magnets. When an external magnetic field B0 is applied, an energy transfer is possible between the base energy in line with the magnetic field and the higher energy level opposing the magnetic field. The energy transfer takes place at a frequency that corresponds to radio frequencies, and when the spin returns to its base level, the nucleus emits energy at the same frequency. The resonant frequency is proportional to the magnetic field at the nucleus. The precise resonant frequency of the energy transition is dependent on the effective magnetic field at the nucleus. The shielding of electrons around the nucleus affects the magnetic field there. The shielding sigma generally reduces the magnetic field at the nucleus and its resonant frequency. The ratio of the increase in frequency Ni to the reference frequency Ni ref is called the chemical shift delta, and is usually small, being measured in parts per million, or ppm. Chemical shift delta equals the difference between the resonant frequency Ni and the reference frequency Ni ref, all divided by the reference frequency Ni ref. You may have noticed something strange in the last diagram, so let's clarify the unusual way that NMR spectra are displayed. We draw most graphs with parameters increasing from left to right. However, we draw NMR frequencies and chemical shifts from right to left for historical reasons. So high frequencies or chemical shifts are to the left, and low frequencies or chemical shifts are to the right. Why do different nuclei have different chemical shifts even within one molecule? The electron shielding is indicative of the chemical environment near the nucleus. As a result, its frequency relates to the nucleus's chemistry. In general, the more positively charged the nucleus, the lower the density of electrons shielding, and the higher the resonant frequency and chemical shift. Most proton chemical shifts fall into the region 0 to 10 ppm, relative to tetramethylsilane or TMS. Acidic protons are slightly positively charged and have a lower electron density around them. On the left of the spectrum, I indicated the weaker electron cloud for the acidic proton by a smaller green patch. Their chemical shift is usually over 10 ppm. On the other hand, if the hydrogen is near an electropositive atom, such as in methyl lithium, electron density is concentrated towards the hydrogen, reducing the resonant frequency and chemical shifts. Here I indicated the denser electron cloud with larger green patches. I wildly exaggerated the difference in the electron cloud density for clarity. Other factors, such as ring currents, anisotropy, and bond strain, affect the frequency shift. Ring currents from delocalized electrons form directional magnetic fields that affect nearby nuclei depending on their orientation. Carbon double bonds and aromatic rings increase the chemical shifts of protons adjacent to them to between 5 and 8 ppm, compared with 2 ppm for aliphatic compounds. The effect of aromatic compounds is directional, so the unusual case where a proton is located over an aromatic ring, the chemical shift is reduced to 0 to 1 ppm. Aldehyde protons have chemical shifts around 13 ppm due to the carbon-oxygen double bond combined with the reduction in electron density. Chemical shift is a measure of the reduction in shielding compared to a reference signal, usually internally in the same sample. Bare nuclei do not occur in solution, so cannot be used as an internal reference. A good reference compound should be unreactive in solution, its chemical shift insensitive to the environment, and give a strong signal. The standard reference is usually tetramethylsilane, or TMS, for proton chemical shift. The standard is okay for routine measurements in a single sample, as long as the reference standard and environmental conditions are clearly stated. However, the chemical shift of TMS varies by more than half a ppm with solvent and environmental conditions. This is further complicated by the fact that under regular conditions, the observed resonant frequency is affected by the magnetic susceptibility as well as the chemical shift. Different solvents have different susceptibilities, and these vary with sample concentration and environmental conditions. As a result, comparison of chemical shifts by comparing resonant frequencies of different samples is inaccurate. The effect of the magnetic susceptibility is the bulk magnetization shift, or BMS, delta Chi. This is the bulk magnetic susceptibility Chi multiplied by a third minus the shape factor, alpha. For an infinite vertical cylinder aligned with the magnetic field, the shape factor is 0. And for a typical finite NMR sample, the shape factor is about 0.006. Delta Chi equals Chi times a third minus alpha. The BMS of TMS vapor is minus 0.01 ppm. TMS liquid is minus 2.23 ppm, and deuterochloroform is minus 3.03 ppm. The chemical shift of TMS vapor is minus 0.36 ppm. TMS liquid minus 0.13 ppm, and TMS in deuterochloroform is 0 ppm. The BMS is added to the chemical shift to give the observed shift, delta obs, and the resonant frequency. Since the chemical shift of the reference is set to 0, the observed shift of the reference is equal to its BMS, so the delta obs is equal to delta plus delta Chi. To measure the chemical shift between samples with different magnetic susceptibilities, one needs to either measure the magnetic susceptibility and shape factor, or find a configuration where the shape factor is 1/3, such that the BMS becomes 0. A sample that is cylindrically symmetrical about the magic angle, 54.7 degrees to the magnetic field, has a shape factor of 1/3 and a 0 BMS. This is achieved using a probe designed principally for solid-state NMR and using special inserts to seal the liquid sample inside a rotor. The chemical shift of other nuclei may be referenced to the signal of the same nucleus. We commonly use TMS for carbon-13 and silicon-29 NMR, but other nuclei need other reference signals. For example, ammonia for nitrogen-14 and nitrogen-15, and phosphoric acid for phosphorus-31. However, there are many NMR-active nuclei, each requiring their own reference standard. Each nucleus has its own chemical shift range. For example, most carbon-13 chemical shifts fall in the range 0 to 200 ppm, relative to TMS. In this carbon-13 spectrum of TMS in acetone D6, we set the carbon-13 signal of TMS to 0. However, it may be preferable to use the proton signal of TMS and multiply it by a standard factor, capital Greek letter Xi, to give the reference frequency for other nuclei. And that means you only need one reference. In this case, the carbon-13 signal of TMS moves to the right to minus 0.9 ppm. However, the chemical shift of TMS varies between solvents. The proton chemical shift of TMS in acetone D6 is minus 0.17 ppm relative to the standard in deuterochloroform. Applying the standard ratio C to carbon-13 TMS signal and all other signals are moved 0.17 ppm further to the right. There are three common ways of referencing chemical shifts. One, relative to the signal of the same nucleus in the same sample. Two, relative to the signal of the proton in the same sample, multiplied by a standard ratio. And three, relative to the proton signal of a standard sample under standard conditions, multiplied by the standard ratio. The standard signal being dilute TMS in deuterochloroform at 25 degrees C under air. To stay updated, please subscribe, get the bell on so that you never miss a video, and order NMR services in the link and in the description. If you like this video, then don't forget to press the like button.